Welcome back. In Unit 6.1 you have already seen this structure of a MOF. This is one of the most popular MOFs and it is called MOF 5. When we want to analyze MOFs, we first need to analyze the separate building units that build the frameworks. And concerning the clusters that constitute the inorganic part of the MOF, we need to ask, what are the points of extension? How many are there? And what is their geometric shape? That means, what kind of polyhedra do they form if we connect these points of extension? Let's take a closer look at MOF 5. It is a metal organic framework that can be prepared from zinc ions and a carboxylic acid. The aromatic system is obviously the organic part. Right now, we will concentrate on everything but this organic part of the crystal structure. We want to have a look at this inorganic secondary building unit, or SBU as it is often called. We have 4 zinc atoms around a central oxygen atom. And these 4 zinc atoms are bridged by carboxylates. They form when the zinc ions react with deprotonated carboxylic acids. In the case of MOF 5, this is a derivative of benzoic acid. One could say it is a dibenzoic acid. It is called terephthalic acid. The carboxylates are the points of extension of this building unit. When you compare this building block with the geometric shape, it would be an octahedron. And the points of extension lie on the corners of this octahedron. And because each organic building block carries 2 carboxylates on opposite sides, the inorganic zinc clusters are connected with each other. And this results in a 3-dimensional connectivity of this compound. Another completely different structure is formed when this very same terephthalic acid is combined with zirconium 4+ ions. This is the crystal structure of UiO66, a MOF that has been developed at the University of Oslo. In UiO66 we see these 12 connecting inorganic building units. This means that this building unit is connected to 12 other building units. Again, a cluster is formed from metal and oxygen ions. If we want to describe the inorganic building unit again as a geometric shape, then this would be a cube octahedron. The points of extension of the inorganic SBU are again the carboxylic carbons. Not every metal forms these large clusters with carboxylic acids. When copper 2+ is combined with the same dicarboxylic acid again, a different cluster is formed. Copper has a high tendency to form dimeric structures like this. This is not only known from MOFs, but also from relatively simple compounds like copper acetate. These dimers have a connectivity of 4. The geometry of this cluster is in many cases square planar, and many MOF chemists compare this shape to a paddle wheel of a ship like this. This is the Mississippi Queen in the harbor of Hamburg. The analogy to the inorganic secondary building units are the blades of the wheel that correspond to the faces spanned by the carboxylate and the copper atoms. Now, if the linear organic SBU is not combined with octahedral or cube octahedral, but with square planar inorganic SBUs, naturally a different connectivity results. For example, a planar 2-dimensional network. What is remarkable about these copper paddle wheels is that they have additional sites available for coordination. In MOFs, these coordination sites are often occupied by solvent molecules, such as water. Or you can introduce another building unit that can bind to the axial positions to connect this sheet of copper paddle wheels to another sheet. And another one, and so forth. These 3 inorganic SBUs are nothing more than a very brief overview of what an SBU is about. It is supposed to show you that the geometry of the inorganic building unit dramatically influences the overall crystal structure. There are hundreds of different SBUs that can be found in MOFs. They differ in the type of the metal ions and/or in the geometry of the clusters they build. In the next unit, we will examine different organic SBUs.